Another interesting variant of quadratic optimization is a set of problems where the quadratic function is non-convex, and the only set of constraints is a box. So you only have lower and upper bounds on variables, and if the objective function was convex, then this would be a very easy, very nice problem, because I mean that's possibly the simplest, one of the simplest set of constraints. So the more interesting case is when Q is not positive semi-definite. If we have bounds on the variables x that are not 0 or 1, then we can normalize it, because this is a quadratic function, and we can easily rewrite Q and B in such a way that all the variables are between 0 and 1. So from now on, we are going to look at a problem where we took the original bounds that were not 0 and 1, and we reduce it to the equivalent problem where x is between 0 and 1. Again, if we introduced the usual auxiliary variables capital Y, then we would end up with this sort of constraint. This time I put the 1/2 in front of the quadratic part of the objective function, because this is what the authors of this work did. And I think it's common in the nonlinear optimization community to have a nonlinear a quadratic objective function that is multiplied by 1/2, and the constraints that are not, for several reasons. So this is simply a reformulation, obviously still non-convex, because we have this nasty constraint here. What we could do is try to simplify everything we can and simply study a set that is our Q set with n plus about n squared variables y, such that y is equal to x times x transpose, and the only extra constraint is that x is between 0 and 1. Obviously, that also means that y is between 0 and 1. The whole matrix is between 0 and 1, obviously. So the idea in this paper is very interesting. It turned out to be already used in another solver, but not published. But the idea is very interesting. It's the idea of using another problem for which many more results are known to try and find a lower bound and an upper bound on this problem. Let's look at the problem and how we would relax it to find a lower bound. So your set of constraints y equals x transpose are bad, and you get a linear relaxation, actually a linear set of constraints through the Markovic inequalities. In matricial form, the Markovic inequalities for the case where all the lower bounds are 0 and all the upper bounds are 1 can be easily written this way. This is a matricial form. If you want to write them down for each auxiliary variable xii and xij, then those 7 classes of constraints are what you need. These are the 3 inequalities that are the Markovic constraint for yii equals to xi times xi, so xi squared. And they form, you can easily say that they are not exactly the tightest possible description of the set xi yi such that yi equals to xi squared, because obviously if xi is between 0 and 1, and so yi is also between 0 and 1, then this is more or less what it's going to look like. Now, the Markovic inequalities, written the usual way, let me write them here, would be very simply yii greater equal li, lower bound on I, which is 0, times xi, plus lower bound on I, again, because this is yii, times xi, minus li times li, li times li, which is all 0. And this is the first one. And then the other Markovic inequality, I don't know if you know them by heart already, but they're usually simple to learn. The other Markovic inequality in the greater than or equal to form is ui times xi plus ui times xi minus ui times ui. All of the ui's are equal to 1, so what you get is yii greater or equal than 2xi minus 1. And that's the one you have. And then clearly you have the other two McCormick inequalities, but they're going to look exactly the same because they're going to be like Lixi plus Uixi minus Uili. And the fourth one will have just Li and Ui flipped over. But this is simply, this goes away because Li is equal to 0. So Yii, let's say, equal then 1 times Xi. And this is the 1. If you plug in for the Yij, you're going to get exactly the same thing. And this, if you remember, that's exactly the constraint we got in the second slide of the very first half hour. So the logical and between xi and xj becomes yij. But this time, these are not integer variables or binary variables. These are just continuous variables. Okay, here's the idea. This set has been studied relatively well, but it's still a continuous set because all the variables are continuous. They're between 0 and 1. The y's are also between 0 and 1. But maybe it's not that well studied. Another polyhedron that has been more thoroughly studied and for which there's a lot of very nice, interesting results is a polyhedron that's a convex hull of a binary set. So a set defined by binary variables. So you won't notice many differences, but the first difference I would like to point out is that these variables are binary. So if you need the convex hull of a set containing x and y such that xij equals to xi and xj, xi times xj, where xi and xj and also yij are all binary, that is a finite set of points, a finite set of binary points. The convex hull of that is going to be a polytope, and it's called the Boolean quadratic polytope, for which several very interesting results exist. The first few pages of this article, the author spent in trying to make the two things match because this is a small detail, but y is defined for I and I here in this definition. The definition of Boolean quadratic polytope, for historical reasons, was only defined for variables y that were not defined for I and I. So we only have yij for I different than j. So we need, first of all, to match the two feasible sets, at least. This is what we do. But first, the most important thing is the following. This is a fundamental relationship between the two sets. This is our continuous set, where all the variables are between 0 and 1. This is the convex hull of a binary set. All you need to do is simply take the convex hull, if you knew it, of course, of Q, project out. So keep only the variables x and yij with I different than j, and you will get the BQP. So all you need is really a projection to go from the convex hull of one to the other. The other, by the way, I didn't underline enough, but the other Boolean quadratic polytope is already itself a convex hull. So it's a convex set. It's a convex hull of a finite set of binary points, but it's itself a polytope. Which is interesting already because it means that Q itself, the convex hull of Q at least, is a polytope too, which is not necessarily automatic given that it's defined on nonlinear, non-convex constraints. And this little detail here about the projection is simply needed again because the two are defined on a slightly different set of variables. So what we do now is the following. Now we try to reduce, if you remember the meaning of the word reducing, the problem Q we have to an instance of a problem BQP, so to speak, in the sense that we need to start with a problem where the objective function contains terms Qii times xi squared, which were reformulated as, were reformulated with variables yii. We need to get rid of those variables somewhat. This is non-trivial. I mean, the whole slide is devoted to it. If you have yii, how do you exactly get rid of it and still get a lower bound? Well, it's relatively simple. You can first of all decompose this initial no longer quadratic function because now it's the sum over I and j of qij times the new auxiliary variable yij. And you can just say, okay, decompose this summation into the summation for all I different than j, and take out this obnoxious quantity that we want to get rid of. That should be relatively trivial. And then now that you have it, take this summation and decompose it again into two parts. One that uses the QII negative. They are perfectly possible because Q is non-convex, so we may have QII negative. And the ones with QII positive. Again, that's a trivial step, right? And now we can say the following. This inconvenient term is equal to, where is it? The sum of two terms, the one with, as we just said here, the negative coefficients and the one with the positive coefficient, which, because these are positive coefficients and because YII is a product between variables between 0 and 1, is itself also non-negative. This thing is definitely going to be non-negative. So if you sum this to a non-negative quantity, you get something that is definitely greater than or equal to this guy over here. So we just removed the non-negative part where, due to the fact that its coefficients are all non-negative. The last step is crucial, and it depends on this thing. So from this summation with YII, what you get is, what can you say about YII with respect to XI? What is the we get rid of it? It's still in the slides. YII is less or equal than XI. This is a McCormick constraint, but it's also very intuitive, and it's due to this. Oh, it's here. This is YII, and this is XI. What can you say about the convex hull of this curve between 0 and 1? Well, definitely it's going to have this secant. So every point xi, YII will be such that obviously YII is less or equal than XI. This is a convex hull. This inequality is always valid, which means what? Which means that this last step is valid as well. So if we take negative coefficient QII and we sum them up with the corresponding YII, this is again an upper bound for the same summation where we replace back the XI instead of the YII. This step is crucial because we really got rid of the YII. We projected them out. We didn't project them out, we just got rid of them by getting a lower bound on the original, on this diagonal term that we didn't want. Which means now a lower bound on the optimal objective function of the initial problem, the quadratic optimization on a box constraint, a lower bound is given by an objective function that I can finally plug into the the Boolean quadric polytope. Because now it only contains terms Yij with I different than j, and xi, where the coefficient now is b bar, where b bar is simply equal to, well, for all the treatment we did here, it should be obvious, but it's equal to bi itself if QII is greater or equal than 0, simply because we didn't have the corresponding YII term. And it's equal to b plus QII if instead QII is less than 0, because we needed to take into account within this summation. So now we have an objective function for our Boolean quadric polytope that we just plug in here. If we formulate this problem, we still have to solve it, and it's still a non-convex problem. It's not easy. It's a problem with several binary variables. So we will need a mixed integer linear software, mixed integer linear optimization software to solve it. But the good thing is that with this change in the coefficients, now we can claim that what we find is actually a lower bound on, well, our purpose in life for these 20 minutes. That is the objective function of the original box constraint quadratic optimization. That's it.